I'm Advait Bopardikar. I'm the practice leader for machine learning and AI for Google Cloud in Canada. So my role is really to play around with customers and come up with ideas in terms of how they can operationalize machine learning on Google Cloud. So today what I want to discuss is the topic of MLOps. I'm sure it's very much top of mind for a lot of people, and it's a field that's definitely evolving rapidly over time. And there's a lot of ways that Google has contributed to the field, but I'm sure there's going to be many more advancements and improvements in this space. Part of our MLOps story is very much so coupled with what we've recently launched in the last couple of weeks, which is Vertex AI, which is a managed machine learning platform really designed for end-to-end development of machine learning. So let's maybe start off with level setting in terms of what MLOps as a concept is. The way you want to think about it is that it's really an engineering culture that blends practices and tool sets that aim about unifying your ML systems development with the ML systems operation. So in the past, we've had this idea of DevOps. DevOps very much so applies in the machine learning space. There's still considerations you have in terms of code and versioning, but then there's also the engineering side of things in terms of scalability, availability, how you can port from one platform to another, as well as things that are always top of mind, especially in an enterprise organization such as security. But the machine learning side of things really adds a couple additional layers of complexity to this. Part of the reason that MLOps as a field is distinct from DevOps is that the behavior of your end system is not only a result of the code that you've developed, but also the data that is used to develop that model and the system that operates it. So in that sense, there's a whole new challenge around governance of data and versioning of data, as well as the features that are derived from that underlying data. There's this process of building pipelines and experimentation. I guess that's the science piece of data science that needs to be resolved. There's continuous training and deployment that's always happening, because no model is ever going to be perfect on day one, or rather, it's not going to continue to be perfect on day 30. It's likely going to require some level of training and tuning and improvements. And as the state of research changes over time, I'm sure you're going to find brand new methods that are either more efficient or more effective that need to be incorporated. But then you also have other challenges in terms of training, serving skew, validating your data, analyzing your models, and then finally the all-important aspect of fairness and explainability and how that overlaps with ethical utilization of machine learning. So combining these two things, that's really where MLOps starts to come out as a practice, where there's some traditional engineering or development or software engineering challenges, but then there's also these brand new data challenges that they need to tackle. So that's really a lot of the impetus around Vertex AI, to provide the tool sets required from the end-to-end machine learning journey, all the way from reading in your data and labeling it, to deploying your training and deploying your models, and actually monitoring and managing the metadata that's associated with it. So there's tool sets that are more AutoML in nature, but then there's also the tool sets required to create a completely custom or bespoke model completely from scratch. So when we think about this MLOps lifecycle, there's multiple different steps, and inside of each of these steps, not only do you need practices in place and systems in place, but you also need the tool set that enables that working culture. So the two areas that I'm going to focus on today is predominantly going to be in the area of continuous training as well as continuous monitoring. So really, thinking about CI/CD when it comes to machine learning. So let's talk about some of the pain points associated with MLOps or machine learning in general. Firstly is more on the experimentation side of things. Machine learning teams need to do a lot of experimentation. And in order to do that experimentation, they need a useful way to track those experiments and compare those runs across each other so they can make key decisions in terms of which direction to go. So to that end, this is where we really bring in this idea of managed experimentation. We provide you all the infrastructure, we provide you the user interface to generate multiple different experiments. They can be various different hyperparameters, they can be various different model architectures, they can be different combinations of features, and you can compare all of those runs in one single user interface. Perhaps you work on a team today where someone will run an experiment, they'll document everything on an Excel spreadsheet, or they'll take a screenshot of TensorBoard and they'll email it to somebody. Gone are those days. More so what we're aiming to do is to provide you the security framework as well as the ease of use to just share dashboards all in one place to go look at experiments, look at the artifacts that were generated from those experiments, the metadata associated with it, and allow for a great deal of reproducibility. So once you're done the experimentation phase, you're on the same infrastructure you would utilize to move into actual training and then finally into the deployment phase. Now, pain point number 2 is around model provenance and reproducibility. Once you've built out your model, you need to be able to see how that model was built, build it out again, and then also in production, be able to understand the chain of decisions that were made that led to a specific prediction. Particularly when you think about regulated environments, sometimes you're going to be in a scenario where you need to prove out why you made a decision and how that decision was made. And that means tracing it all the way back to an experimentation run that may have happened months ago and understand how the data led to a model, and a model that led to a final decision. So that's really where this next piece comes in around pipelines. So Vertex Pipelines allows you to define a pipeline, so various different components for your various different machine learning steps, either in a Kubeflow pipeline format or in a TensorFlow Extended or TFX format, and then deploy those pipelines on a serverless infrastructure. So what I mean by that is you're no longer worried about, does my machine learning engineer or my data scientist know how to maintain and manage a Kubernetes cluster? You can just focus on the pipeline required for the machine learning task at hand and focus on what is core to your skill set rather than being pulled in far too many directions. I know in a lot of organizations, especially in startups, many times you're wearing multiple different hats, and that can be challenging at times, but is sometimes necessary. Our intention is to make machine learning considerably easier as a general platform, meaning that you can have those defined roles and responsibilities to eventually scale out to what would be a far more, let's call it mature data science or machine learning team. So inside of a pipeline, you'll be able to visualize it through a DAG or directed acyclic graph. And inside of each step inside of the pipeline, you can see not only the artifacts that were generated, but the lineage of how the data traversed into that pipeline, generating each of those artifacts. So from an audit and governance perspective, you get that full visibility of your pipeline end to end. Now, for those of you who where this idea of a pipeline is somewhat novel, let's maybe do a bit of a 101 on what a pipeline is. So inside of a pipeline, you're really building up multiple different steps or operations or ops inside of it. And you can think of these as the key steps that make out your machine learning solution. So first step may be about extracting data from a data source, validating that data to make sure there's no anomalies in terms of the distributions of that data, doing certain preparations, which could be feature engineering or cleanup of that raw data, eventually training that model, evaluating that model, validating it, and then finally, once it meets certain thresholds, blessing that model so it can be deployed into a production environment. Your first run of this pipeline, hopefully is straightforward enough, but eventually you need to make sure that this is built out in a way that you can reproduce and recreate this and trigger these pipelines on an ongoing basis to push updates to a production environment. So each one of these operations is created as a function that can be containerized. And each one of those containers is then orchestrated into a pipeline that has dependencies on each other. And in the Google Cloud sense of things, each one of these containers is deployed onto our container registry. Now, each one of these steps can also offshoot to other serverless or fully managed solutions that can do some of the computation on your behalf. So for example, instead of doing the actual training on your pipeline infrastructure, you can offload that to Vertex for doing fully serverless training and serving. When it comes to doing data transformations, you can use Dataflow, which is really just a managed version of Apache Beam, to do both streaming and batch ingests of data and data transformations at high parallel scale. Then finally, the artifacts that are generated from this pipeline can all be stored on a common blob storage location on Google Cloud Storage, so they can be referred in the future with a high degree of durability. Now, one of the key pieces of a pipeline is the metadata that you generate throughout of it. And again, our intention is to make this as easy as possible, and we're going to continuously develop these functionalities when it comes to metadata tracking. Today, we provide a very simple Pythonic SDK, meaning that it's as simple as specifying which object of logs you're saving, as well as metrics, and providing a name and a location for those logs, so they can be referred in the future, as well as visible inside of that DAG representation. It's really intended to make it as easy as possible for data scientists to put in a language or a format that they're probably already comfortable with and limit the amount of customized development that you otherwise have to do. Now, once you've generated all that metadata, once again, you have that lineage of exactly how the data traversed through that pipeline, the artifacts that it generated, and doing this on a time slice basis. So each run of a pipeline has its own set of artifacts associated with that run. So you can see how your model was generated in May and compare it to how it was done in July and see what changes have happened over that time period based off of changes either in your model, your feature distributions, your data set, or the general approach that you're taking. So now the final piece of today's conversation, and today's really meant to be a bit of a high level understanding of these technologies. By no means am I getting completely in depth with all the different technologies on Vertex, but let's start talking about model monitoring. Now, a common challenge you're going to have is, why did my model all of a sudden stop working? And this is quite common in most models, especially if you're looking at time series models, but this is true in other regression or classification problems, where your models start to get stale over time. Over time, the data set that was utilized to train your models no longer seem representative of the data that's seen in production. And it's an example of where you see degradation that impacts the performance, and eventually is going to impact the end user who's consuming that model. So it could be an automated decision that's shifting over time, that's reducing the user experience, or it could be something that's changing the user behavior based off of the user behavior, and meaning that the user is not getting the right suggestions or the right user experience at the very end. So the two silent killers that I really want to discuss today are the idea of skew, or more specifically training serving skew, as well as drift or prediction drift or data drift. These two ideas, very similar in nature. There's a little bit of an overlap in terms of how you may think about it, but there are some subtle differences in terms of what defines one over the other. So let's talk about training serving skew first. Here's a very simple example in terms of thinking about it. You may have a data set that was completely trained on green bananas to do classification and identify an object. So that's great. Your model performed perfectly well when it came to training and evaluation and testing. It does a great job of identifying green bananas. But in production, when you start to deploy it, what you start to find is that the bananas you're actually identifying tend to be yellow. Well, this is an example of training serving skew, where the distribution of your training data set and what you actually see in production on day one are completely different than each other, meaning that you're going to see performance problems that may lead to a model underperforming than what you've seen inside of the data science workbench environment. Prediction drift, slightly different. It's more about the change of that data distribution over time inside of the serving environment. So you may have a model that was trained on green bananas. In production on day one, it seemed to see a lot of green bananas, but over time, as bananas starting to ripen, you start to see more and more yellow bananas inside your training data, or inside your serving data set, meaning that there's a shift in terms of what has happened in the serving environment over time. And what prediction drift is intended to do is to identify that shift is happening, to trigger a training job, so you can take a brand new augmented data set that has a broader, more representative feature set of your production environment, and then retrain your model so it can perform better with this brand new data distribution. So that's really where the model monitoring capabilities of Vertex come in. It's intended to automatically alert you on when changes have happened, either because of drift or training serving skew, and provide you an automated pipeline to retrain your models and eventually evaluate those models so you can make the decision to make a push to production or not. So we'll provide you the statistics around those feature distributions, understand what's happening inside of production, and then allow you as the data scientist and machine learning engineer to finally pull the trigger on making an update. So how do you actually detect these two things? When it comes to skew, it's really as simple as providing the baseline statistics of the data set that was used for training your model. Now, when it starts to make predictions in production, we can compare the distributions of your training data set to your production data set and see whether or not they overlap in a way that would lead to the appropriate expectations in terms of prediction accuracy. When it comes to drift, it's slightly different. What you're doing is you're comparing the distribution of features in your serving environment on day 1 to day 2 to day 3 to day n. You're trying to see, has that changed fundamentally over time, meaning that there's either a change in terms of the data that you're ingesting or user behaviors that's going to likely change the outcome of your predictions, meaning that you're more likely to actually make an error in your models, which would be the key trigger for saying that it's now time to actually make a retraining job for our models so we can make improvements in production. Now, there is another important piece to this whole model monitoring piece, and I heard the tail end of our previous presenter kind of mentioned something around feature importance, and that's really where our explainable AI toolset really come in. So the intention of explainable AI is to allow you to understand which features are most important in terms of making a decision. So once you've trained your model, you'll get a result of your feature statistics, which tell you which features were most important in terms of the weights that led to the building of that model. But the same thing is also applied when it comes to each independent prediction. You'll get a score in terms of which features most led to that final end prediction. And this applies not only to differentiable, but as well as non-differentiable models, which may apply slightly different approaches. So whether it be an integrated gradient or what we call X-ray, as well as a sample Shapley approach, that really depends on your model. Today, inside of Vertex, we'll apply a different approach depending on the model type. So I know that's a very much a rapid fire in terms of ML ops and some of the considerations, by no means all of the considerations. I guess where I want to end off is to point you to a white paper that we've published in the last, I think about a month or two ago, that goes into the continuous delivery and the automation of the MLOps framework for machine learning, both on Google Cloud, but also just as a generic concept that's really platform agnostic. So feel free to look for that guide. It's completely free online, and hopefully that goes into a greater level of detail that can help you as you guys develop your own MLOps journeys. So,
I wonder if skew and drift are issues that can be avoided using training data better well distributed or of better quality.
yeah, it certainly is. It's something that you should be watching for and monitoring as much as you can, even before you deploy a model. But the reality is that you're going to see changes in that distribution over time. So a good example of this, I mean, maybe not a great example, but you're going to expect that sometimes you're not going to have training data sets that are representative of the real world. Perhaps you're generating synthetic data. Perhaps you're using data sets that are well known, but aren't necessarily representative of real world environments. You want to try to look at those data distributions, but it's hard to know what the real world is like until you actually start. So in many senses, you want to think about your data collection strategy. You may deploy a model that you know full well is going to do mediocre because the original training data set was not representative of the real world. But over time, you're going to collect additional data points that allow you to create a feature set that's far more representative and make improvements from there. So don't necessarily feel the need to go into production with a model that's perfect. Sometimes it's part of the data collection strategy to start with something that's good enough.
One of the topics that keeps coming up is the number of ML projects that fail. Obviously, it's a really high number, so we say 80 to 90% kind of thing. Would love to get your thoughts on maybe potentially why you think that is, and to all our budding machine learning engineers and data engineers out there, maybe any advice that you could give to people in the audience on how to improve the success of those types of projects.
Yeah, for sure. So I think the number I've seen is somewhere around like 83% of ML projects fail. I think it's a combination of a couple things, some of which are technical in nature, meaning that you've not really gone through the process of collecting the appropriate data, or rather high quality data to actually train a model to get the level of performance that you need. There's another technical aspect, which is once you've deployed model number one, do you really have either the infrastructure, the tool set, or the practices in place to continuously develop and monitor them and improve upon them over time? But then the last piece that I want to mention is not really technical at all. And the reality is every project is embedded in terms of some sort of business context, especially as you get into larger, more enterprise organizations. There's a lot of politics that you have to figure out in terms of, can we even reasonably explain to our stakeholders who are going to make the final decision to deploy a model how this model works, why it's beneficial, how to take on the risk of being a probabilistic system as opposed to something that's deterministic, and what impacts can happen there. So there is an inexorable link in terms of business outcomes and justifying your model, as well as the actual pure statistics and software development around building the model itself. So I think it would be wise for a lot of practitioners to think about both aspects, not necessarily hone in just on one, unless you're in academia and you're focused on research, then you're really just focused on the technical side of things.
How do you deal with data bias?
I think that's maybe a broad question, because there's many different types of data bias and ways to think about it. So you can think about data bias where you just don't have data that's fully representative of the world, or you may have data that has some implications which may be inherently biased based off of human decision making, and you may just have data sets from a small sample that you need to augment over time. One of the tools I would suggest into that is what we call the what if tool. I believe it's an extension of TensorBoard. It allows you to look at different slices of your data. So for example, you may want to see, is my model notably underperforming with specific either gender or ethnicity groups? You may find that the reason for that is your data set is overweighted on one subset versus the other. So when I'm thinking about bias in this scenario, I'm really thinking about it more from a societal perspective. But then there's also just the purely statistical basis of it, which is, can we look at the data distributions of our data sets? Do they seem to be representative of what we see in production, or in the real world? And do we just need to collect additional data that has, otherwise is devoid of any social implications, but is from a mathematical perspective biased?
the Vertex pipeline and if it's available now? Can we use the
Yeah.
Vertex pipeline now?
So if you go onto Google Cloud and you go into Vertex AI, you can use pipelines, meaning you can author a Kubeflow or a TFX pipeline, deploy it to serverless infrastructure. On Vertex, you'll also see notebook environments. You'll see experimentation environments, training, serving infrastructure, feature stores, various other capabilities that your data science team would likely